Okay, guys, welcome back to the final part of lecture 3 on transformer. Okay, we see that we have this as a steady state equivalent circuit for the transformer using phasor. Okay, so this is called the exact equivalent circuit because we are trying to we're trying to simulate all the real condition in the transformer. However, if you do some hand calculation back in about 100 years ago, we don't have any calculator. Okay, so calculating by hand is quite difficult if we use this equivalent circuit. Therefore, we uh, accept some small error, but we make it easier by using the approximate equivalent circuit. Before we move that, I need to tell you just one more thing. We can refer the primary side to the secondary side, which is the circuit we saw already, or we can do secondary side refer to the primary side refer to secondary side on this diagram. So here V1 and I1 will be refer to side 2, and then you will have this equivalent circuit. So we say a quantity can be referred to winding 1 or winding 2. Now, as I said, you can make it easier by moving this magnetizing branch, including RC1 and JXM1. We can put them instead of here, we can put them up here. So we now have 3 branches in parallel. This one, we have 5 components in series, and you can just calculate it one impedance, one complex impedance. Here we have another in parallel branch, another in parallel branch. And that's why in chapter 2 I told you that we may have to look at AC circuit with 3 parallel branch. So this is the case. Okay. Now we combine all R1 and A square R2 into R1 EQ. Okay. And we also combine XL1 and XL2 into X1 equivalent. So XL1 plus A square XL2 will give us that. Okay. Now, if we have a real transformer, how do we know about these parameters? Okay. So for transformer, we can do some tests, and from those tests we can determine the parameter of the equivalent circuit. Okay. So we need to perform 2 simple tests. It's called open circuit test and short circuit test. Okay. In power transformer, we will call one winding with higher voltage, the high voltage winding, and the other one will be the low voltage winding, so HV and LV. Okay. To perform the open circuit test, we will increase the voltage slowly until we reach the rated voltage, and we will measure the current going through the low voltage coil. Doesn't matter if it's primary or secondary, we just use the lower voltage. So we put full voltage on the lower voltage, and we measure the real power watt, the current, the RMS current, and the RMS voltage. Okay, so we will have this equivalent circuit. We open circuit the second coil, so we only have those. Okay, and you need to perform 4 steps to calculate the quantity, the RC and XM here. Okay, so we have VOC, IOC, POC are the open circuit quantity we measure with those 3 meters. So the first step, we calculate RC, which is VOC squared divided by POC. Next step, we calculate IR. IR is the current component going through RC. By dividing VOC by RC, calculated in step 1. And then the IOC phasor will be the IR plus IX. Okay. Therefore, we can calculate IX. We measure IOC. We measure the value. So these are complex value. So we need to convert into the magnitude calculation and find in step 3 we calculate IX, which is equal to this expression, and then finally divide it VOC by IX to get the XM. And we say these RC and XM are referred to the LV side because we did the test on the LV side. On the now another test is called short circuit test. Now we do the test with all equipment on the HV side, and we short circuit the LV side. Okay, short circuit the LV side here, and we varying the applied voltage very slowly from 0 until we have the rated current in the HV side, and then we will read all three values VSC, ISC, and PSC. And now the equivalent circuit would be something like this: a voltage source in series with REQ plus JXEQ. So here it's shorter, it's more straightforward to calculate the REQ, which is that with this expression, and then step 2 we calculate the ZEQ, and then finally we calculate XEQ. Remember, REQ, XEQ are referred to the HV side because we are measuring everything on the HV side. Before we can use these, you have to refer either REQ, XEQ to the LV side and draw the equivalent circuit on the LV side, or you have to refer RC, XM to the HV side and draw the equivalent circuit on the HV side. And remember, by doing these circuit tests, we can only form the approximate equivalent circuit. So in example 3.9, we are given the OC and SC test reading. So three quantity in each testing, and then we need to find the equivalent circuit parameter refer to the HV side. If they refer to the HV side, it means the open circuit test data would need to be referred to the HV side. Okay. So first, from open circuit test, we perform 4 steps, and we get these values RC, XM. And the short circuit test we do, and therefore we can calculate REQ, ZEQ, and then XEQ. Okay. And now we will talk about some performance indicator for transformer. For each machine type, we will need to check the performance indicator. So for transformer, we have two performance indicator. Efficiency is one, okay, and voltage regulation is another. To calculate the efficiency, you always calculate the output power divided by input power. So that's called efficiency. Theta is the output power divided by input power. And if you are given output power, then the input power can be calculated by adding all the losses to output power to form the input power. Okay. So that's the efficiency calculation. Here PC is the core loss, and PI is the iron loss. If you know the input, then you can calculate the output by taking out the losses from the input. So take out the copper loss and also iron loss. The second performance indicator is the voltage regulation. It is defined as the ratio between this expression V no load minus V load and divided by V load multiplied by 100%. So that's the end of part 3 of lecture 3.